Hey, let's take a quick look at the power rule, the really most basic little piece of calculus. Most people don't really struggle with it, but it's really, really important that we have those methods down and we don't make careless mistakes with them. So it's worth taking a look at, even if it's not particularly difficult. Might throw in something in there that might clarify something for you, but I just want to make sure everybody's very comfortable with the mathematics. So let's kick it off with a quick, simple problem here. Now, remember power rule. And I tried to motivate this in class with a long reason as to why this works. But effectively, what we know is that if you have a function that is ax to the n, where n is basically any real number, that's really important. We really motivated it through the polynomial where n had to be a 1, 2, 3, 4, 5, etc., a nice little whole number. But in reality, it could be a decimal or a fraction or any number we really want it to be. And so the power rule simply says that if you take the derivative of f, you would get n multiplied by a, and then our exponent is going to simply reduce by 1. That's the power rule. And because a derivative is a limit, if we have extra functions and we added b with some other value out here, then we would just keep going. We would do b times m and then x to the m minus 1, and we could add as many terms as we wanted that are separated by pluses or minuses. Now, as far as if you wanted to multiply two things together, that is a story for a later time. That is not going to be the power rule. That would be called the product rule. That's going to be a little more complicated. But I thought we would just go over a couple of quickie little questions on that. So my first one would be 3x squared minus 4x plus 5. Now, again, every calc student hopes that their teacher would be kind enough to ask a question this simple on the test. They're usually disappointed because we don't usually ask questions at that level. But a derivative of this would be easy. 2 times 3 is 6. We're going to decrease the exponent from a 2 to a 1. Here, this is 1 times 4, which of course is 4. This is x to the 0, but x to the 0 disappears, and the derivative of any constant, remember a constant's a horizontal line whose slope is 0, so it's gone. So I have a simple, quick derivative. Now, what I wanted to do on this is quickly go over here and look at Desmos and just kind of clarify a little bit about it. So in Desmos, I have myself my little parabola right here. And you'll notice that we have this nice little parabola looking like this. I know that it has a vertex right down here at 2/3, right? So at x equals 2/3, that's the place, that's like the vertical line. That vertical line would cut right through that vertex. Now look at what happens. To the left of that vertex, the function is decreasing, so its slope is negative, and to the right, it is increasing, so its slope is positive. So I went ahead and I graphed its derivative here, and what you'll notice is the portion to the left of 2/3 has a negative derivative. Now notice its slope is positive, but you don't want the slope of this one. This is the slope. So you'll notice the slope in blue is being represented by values that are below the axis. So this blue line is below the axis because the original graph had a downhill slope, and the values above 2/3 is increasing, and therefore that representation is above the axis. Pretty simple little expression, huh? Okay. So let's go ahead and take a look at the second example. We just have a couple to do. So my question 2, I decided to make it a little bit more robust, but not by any stretch anything anybody would be too scared of. But this would be more in line with a question that might likely be asked on a test in a calculus class. You know, we got some fractions now. But I did design it to be very, very kind because, of course, if I multiply 3 by 2/3, I got 2x to the second. Multiply 2 by 3/2, I get 3x to the first. 1 times 2 is 2, and this would be x to the 0, and the derivative of that is 0. Now, this would be the answer to the derivative, but I did want to look at something. So what I noticed is if I were to factor this derivative, I would have the following story. I'd have 2x minus 1 times x plus 2 if I factored it. Now, where would the derivative be 0? It would happen at positive 1/2 and at negative 2. Now, remember, if the derivative, if g prime of 1/2 is 0 and g prime of negative 2 is 0, the only way that a slope would be 0 in this graph is if there is some kind of a extrema, a max or a min that is happening and at those values. We could also organize it as a quick decision chart, or we called it the sign graph method, knowing that it was 0 at these places, and it looks about like that. Again, this is what the graph of G prime. Now, what I can see then about G prime is that the graph should have been increasing, going uphill through negative 2, and then it goes downhill from negative 2 to 1/2. Well, if it was increasing and then decreasing, I think that would probably seem to indicate that that value would be a maximum, a local max. Then it goes downhill for a period of time until it reaches 1/2, and then it goes back uphill. So at 1/2, that should be some kind of a minimum value. So, and then it's going to be increasing again for the rest of the domain of the graph through infinity. So let's go ahead and again, let's open up Desmos and let's take a quick look at that particular graph. I don't think I turned one of these off, so let's do that. So Q1 can go away. So let's take a look at our first graph. So notice I have this nice little deal. I've also got my parabola. Notice that if we look right here at negative 2, that's the place where the parabola crosses the x-axis. The 0 of that perfectly lines up with the maximum of the curve. See it? Here, where 0 on the derivative of parabola, it would again line up with the minimum of that curve. So understand the roots of one is telling me about the extrema of the other. And again, if we hide this, we see it was increasing through negative 2, decreasing from negative 2 up until 1/2, and then increasing for the rest of the domain through infinity. So hopefully not too bad. Okay, so scooting on to number 3, we're getting most of the way through this thing. Let's go ahead and make one that's maybe a teeny bit harder. And I was thinking about doing something that's a little bit crazy here. How about this one? This would be a harder problem. So imagine now we had j of x being 2 over x cubed. Then we had plus 2x. And then we had plus the square root of x. So now that's a whole lot of stuff. Now, the first things first is that isn't set up to look like power rule is supposed to be looked at. So what I'd like to do first is rewrite that as 2x to the negative 3 plus 2x plus x to the 1/2. The first thing we want to do is we want to make it look like power rule, which is ax to the n or ax to the k power. So this didn't look like that, nor did this. So I wanted to explicitly make that happen. So when I look at j prime, I would get negative 6x to the negative 4. 1 times 2 is 2, x to the 0, but anything to the 0 is 1. And then I have 1/2 x to the negative 1/2. Now, this is a good answer for a derivative, but I will say most of the time people feel more comfortable expressing it this way. I would do negative 6 over x to the 4th plus 2, and then I would be 1 over 2 square roots of x. Now, that looks like kind of a mess, but the nice thing about that we can see is we definitely know that the domain says x can't be 0. That is definitively true, because it would be an issue right here. And also the domain is that we can only have values above 0. So the original function's domain is x has to be greater than or equal to 0, but the domain of the derivative is that x has to be strictly greater than 0, which is a little bit interesting. I can't actually take the derivative at 0. And the reason why is a derivative is a limit, and it must be able to be approached from both sides. And since the graph ends at 0, and goes towards the positives, I can't approach that from the negative side because that would not be in the domain. So kind of a weird story, but as we look at it, what we would see is that there are regions where the graph has a downhill slope and places where it has an uphill slope. And so I don't know that this is going to be the most enlightening version of this, but you know, I want to be consistent. So here we go. Here is the Desmos on that thing. So we have our original function. I took my derivative, and just for fun, I left some of it in the uglier form. But what we can see right here, we do have a place where that graph has a local max or min, so it was decreasing to that value and then increasing beyond that value. And what we'll notice is if we graph it, we will see this place where this is 0. We'll see this place where that's 0. Notice they're the same thing. Where that 0 happens in the derivative coincides perfectly with those max and mins. Notice the derivative is negative, meaning it was a decreasing followed by increasing function. So if that's true, a decreasing followed by increasing would mean that that decrease to increase would be in a minimum. And if you look at the green graph, you see that we do in fact have a minimum. And notice that those line up perfectly. So again, the sign graph method would tell me that I have a downhill followed by an uphill, meaning that this guy right here would have to be a minimum. Okay, last little question that I have for you. Let's go ahead and stop share, and let's go back here to this. Actually not intended to be a hard question by any stretch at all. I was going to go super easy with you for the last one and look at, let's say, n of x being the square root of x, or x to the 1/2. And so what that means is n prime of x would be 1/2 x to the negative 1/2. But what I would like to do with that is just do one extra little piece, and let's find the tangent line at x equals, say, 4. Now keep in mind, for a line of any kind, we need a slope and we need a point. So when we refer to the point, we're always referring to a point on the original curve because it wants to touch that curve. So of course, if I plug in 4, I am going to get 2. So I could write my point slope form right here. But then, of course, if I want to find the slope, that would be coming into the derivative. So keep in mind that if I wrote it this way, that's fine, but it's a lot easier to think of it in that way. And so what I find is that if I plug in 4, the square root of 4 is 2. 2 times 2 is 4. So I have a slope of 1/4. So if I was going to look at the graph of this thing, I should see it perfectly glance right across that curve and intersect it in exactly one place. And let's see how we did if we came up with a nice equation of a tangent line. So here we go, back to our story. I'm going to go ahead and turn off of Q3 here. Here is my function. Here is the point 4,2 that we said we would like to have. And so now let's see if we did y minus 2 equals, let's say, x minus 4. Notice that would be a line for sure that covers that, but its current slope is 1 because I don't have anything in front. But we just figured out that we wanted a slope of 1/4. And you would notice that we have a nice, perfect story there. And the last little piece to mention here is if we grabbed this and we copied it down here, and I changed this by making it opposite and reciprocal, that would make it perpendicular. So that would be -4. That is actually what we're going to refer to on our course as a normal line. So that is the normal to that curve. And hey, there's the power rule. I will see you back in class. Hopefully that's a simple clarification, pretty easy set of problems. I'll see you later. Bye-bye.